The holographic universe. Are we living in a 2D projection? The signal arrived all at once. High-energy photons from a galaxy billions of light years away, stacked so tightly our instruments should have seen a delay. They didn't. Every color hit together as if space had no texture at all. But here's the twist. If the universe really has pixels, if there's a smallest step, it should leave fingerprints in that light. So why didn't it? Because the place where answers lie sits past our current tools. Beyond atoms, beyond protons, down where gravity and quantum punch through the floorboard. The Planck length. If we could cross it, we might learn whether space is smooth or an elegant lie. Our rulers, our clocks, our blind spots. We grew up measuring the world with ourselves. A foot, an arm span, a day around the sun. Those worked until they didn't. Telescopes pushed our eyes outward. Particle beams drilled inward. And somewhere between galaxies and quarks, our rulers and clocks started failing in opposite ways. Einstein gave us a new ruler, spacetime as a smooth fabric. Gravity wasn't a pull, it was geometry. The sun dents the sheet, Earth follows a curve. In that picture you can zoom forever. Have a distance, then have it again. No last stitch in the fabric, just finer coordinates. Quantum mechanics gave us a different kind of ruler, one with teeth. Energy, angular momentum, even the light from a hot stove come in packets. Not any frequency, specific notes. Electrons sit on steps, not ramps. And when you try to know both where a particle is and how fast it's moving, nature answers with a limit. Push one, you blur the other. So which story is right? For most of life, both. GPS satellites trust time dilation to get you to the right street. Transistors trust quantization to play your music. Each theory rules its neighborhood. The problem shows up where neighborhoods overlap, where something is both incredibly small and unimaginably heavy. Black hole cores, the universe in its first instant. To talk there, you need all three constants that define the deep structure of nature. The speed of light, see the strength of gravity, g, and Planck's constant, h-stroke. Put them together and you can build natural units. No feet, no seconds, just the universe's own yardsticks. The Planck length, about 1.6 times 10 to the minus 35 meters. The Planck time, the tick it takes light to cross that length. These aren't inventions. They're what fall out when you combine our best measurements of motion, gravity, and quantum grain. Now get this, try to look smaller than that length and the act of looking breaks your lens. To resolve tinier details, you need higher energy light. Higher energy curves spacetime. Curve it enough in a region that's small and you don't get a picture, you get a horizon. You've made a black hole where your microscope should be. Add energy, the hole grows. The image recedes. That's our blind spot. Not ignorance by choice, but a wall built from the very rules we trust. It's also a clue. Several frameworks chase this edge. Loop quantum gravity says space itself is woven, areas and volumes come in indivisible quanta. String theory says particles are tiny strings whose size smears any attempt to pinpoint. The holographic principle hints that information inside a region lives on its boundary, like pixels per Planck area. We've come as far as biological rulers can take us. The next step isn't longer tape. It's a new language for space and time. The Planck trio, length, time, energy. Start with 3 numbers and you can rebuild the world. C sets the ultimate speed, how fast light and causality can move. G tells you how strongly mass and energy bend spacetime. H-stroke fixes the grain of quantum action, the size of the smallest kick nature will allow. Combine them and 3 natural scales drop out without asking our permission. A length, a time, and an energy. They're not opinions. They're the only numbers you can write that survive a meeting with aliens. The length is the Planck length, about 1.6 times 1035 meters. You can't draw it. You can't even cheat. If an atom were blown up to span the visible universe, a Planck length would be a single tree inside that universe. It's the scale where quantum fluctuations of fields are so intense that their gravity can't be ignored. We called that a blind spot earlier, but think of it as a threshold. Below that, Distance stops behaving like a number you can have forever and starts acting like a count of fundamental units. Then there's the Planck time, roughly 5.4 times 1044 seconds. It's the time light needs to cross one Planck length in a vacuum. In that blink beyond blinks, our best theories won't cooperate. General relativity tries to assign smooth coordinates. Quantum theory demands jitter. The result is a foam of possibilities, virtual particles rising and fading, each altering curvature enough to scramble the very clock you're trying to use. Try to mark events closer together than a Planck time, and your marks dissolve into statistical noise. The third is the Planck energy, often introduced via the Planck mass, about 2.2 times 10^8 kilograms. That sounds laughably large for particle physics until you realize it's the energy scale where a single quantum self-gravity becomes non-negligible. Pack a flea egg's worth of mass into a region approaching the Planck length, and you're flirting with horizon formation. Translate that mass to energy, and you're near 1019 electron volts. That's 19 orders of magnitude beyond the Large Hadron Collider, enough to melt every force we know into something simpler. These three scales aren't decorations. They triangulate a boundary. The Planck length limits how finely you can carve space before gravity answers back. The Planck time limits how quickly you can stack events before causality blurs. The Planck energy limits how hard you can kick a system before your kick turns the lab into a black hole. Together, they fence off a patch of reality where smooth spacetime and quantum fields on a stage both stop being useful metaphors. There's another way to see why these numbers matter, and it's less mystical than it sounds. To resolve a smaller feature, you need shorter wavelength light. Shorter wavelength means higher frequency, which means higher energy per photon. E equals h stroke omega. Pour enough energy into a tiny region, and by E equals mc2 you create mass energy density. Curvature follows. Push past the threshold set by G, and the region traps its own light. Your microscope collapses into the thing you were trying to inspect. That failure doesn't say stop asking. It says change the question. Now turn to the early universe. Roll the clock back to when the Hubble radius was measured in Planck lengths, and the only sensible timescale is the Planck time. Before one tick, the forces we separate in textbooks likely hadn't separated at all. Electroweak unification happens far below this energy grand unification. If it exists, higher, and gravity's seat at the table becomes unavoidable at the Planck scale. That's the edge of our lawful knowledge, not because physicists ran out of nerve, but because every attempt to write equations there, with C, G, and H stroke all loud, returns infinities that mean your language is wrong. Loop quantum gravity takes the hint literally. It predicts smallest non-zero eigenvalues for area and volume, quantum measured in units built from those same constants. Spin networks evolve discretely. A surface's area is a sum over Planck scale tiles. Time advances in steps on the order of a Planck time, not as a syrupy flow. String theory walks in differently. It replaces point particles with strings whose characteristic size is around the Planck length, smearing interactions so point-like stops making sense. Either way, the Planck trio polices the boundary. You can't probe smaller than the probe, and the probe size is set by H stroke, C, and G. What about evidence? Those photons in the cold open told us something sobering. If spacetime were a crude lattice, high-energy light would stumble while low-energy light glided. Gamma-ray bursts from billions of light years away didn't show that stagger. Within our current precision, Lorentz invariance holds. That doesn't kill discreteness, it narrows how it can hide. Any acceptable theory has to give you a grainy microstructure that looks perfectly smooth from far away. The way water looks continuous though its atoms all the way down. Here's the psychological turn. The Planck trio doesn't just cap our rulers, it caps our imagination. We're trained to think smaller reveals truth. At this frontier, smaller is not a path, it's a trap. The next reveal isn't beneath the Planck, we've hit the floorboards. It's in how the boards are laid, how information, geometry, and causality conspire to make space appear. And those three constants are the only clues on the table. Where continuum physics breaks, singularities and infinities. Follow the smooth fabric long enough and it tears. That's what a singularity is in general relativity, a place where the math says curvature blows up, density goes to infinity, and the coordinates you trusted fall apart. It isn't a point you can visit. It's a sign nailed to the road that reads, your map stops here. Black holes are the clearest example. Solve Einstein's equations outside a spherical mass and you get a horizon, a region from which light can't escape. Keep evolving inward with that solution, and the model drives you to a central singularity where spacetime pinches to zero volume. Infinite curvature is just the theory's way of saying it can't continue. We meet the same wall if we rewind the universe. The Friedmann-Lemaitre, Robertson-Walker solutions describe an expanding cosmos. Run them backward and scale factor shrinks to zero, temperature and density soar, and at a finite proper time in the past you hit an initial singularity. We call it the Big Bang in shorthand, but the bang is really the breakdown. At that boundary, the assumption that spacetime is smooth and differentiable, Einstein's starting point, no longer holds its weight. Infinities are not trophies, they're warnings. They tell you you've asked the right question with the wrong language. Quantum field theory learned this lesson the hard way. Early calculations spat out infinite self-energies. The fix wasn't to pretend away the infinities. It was to absorb them into redefined physical parameters through renormalization, leaving behind finite predictive answers. That worked because the fields lived on a smooth background that didn't react to their jitter. Gravity is different. Energy curves spacetime, and quantum fluctuations carry energy. At very short distances, the fluctuations that make quantum theory tick should twist the very stage on which the theory is performed. Try to quantize gravity as just another field on a static arena, and the integrals don't merely run large. They explode uncontrollably. Non-renormalizable is the technical verdict. Translated, your rules aren't designed for this arena. You can see the clash physically. To probe a region, you raise the momentum spread of your probe, shorter wavelength, higher energy. Higher energy means more stress, energy density in that region. In general relativity, stress, energy sources curvature. Crank it high enough in a tiny volume and you don't refine your image. You dig a gravitational well deep enough to hide the region behind a horizon. The continuum promises you can have forever. The gravity that enforces reality says there's a threshold where having triggers collapse. Even information throws a red flag. Black hole thermodynamics tells us the entropy, the information capacity, of a black hole is proportional to its horizon area measured in Planck units, not its volume. That's Beckenstein-Hawking's result. It's a precise equation with c, g, and h stroke right in the coefficients. If the interior were a continuum with infinite degrees of freedom per cubic meter, you'd expect capacity to scale with volume. It doesn't. Nature is counting bits per Planck area, which hints the continuum is a mirage at high resolution. The black hole information paradox sharpens the knife. Hawking radiation, derived from quantum fields near a horizon, looks thermal featureless. Let a black hole evaporate completely, and you've apparently turned a pure quantum state into a mixed one. That breaks unitarity, the backbone of quantum predictability. So something gives. Either information isn't lost and must be encoded in correlations we don't yet know how to track, or our description near horizons is missing a layer. The holographic principle answers. The information isn't gone. It's stored on the boundary in Planck-sized patches. That's not mysticism. It's an accounting rule born from singularity physics refusing to let continuum assumptions pass. Singularities also haunt cosmology's opening act. If the Big Bang was a true singular beginning, classical causality ceases before the Planck time. Questions like, what happened before lose meaning because before presumes a clock that hasn't formed. Loop quantum cosmology proposes a different picture. Quantized geometry replaces the singularity with a bounce. As densities approach Planck values, A repulsive quantum geometric effect counters collapse. Not proven, but it's a concrete way discreteness cures infinity by never letting scale factor reach zero. String theory offers another mechanism. Extended object smear interactions that would otherwise pile up at a point. Dualities relate short distances to long ones, hinting that smaller than Planck maps to larger than Planck in disguise. Again, the cure for the infinity isn't cosmetic, it's structural. You remove the illegal question, what happens at a point of zero size, by declaring point is not a meaningful word in your ontology. And yet, our instruments keep testing the smoothness at accessible scales. High-energy gamma rays arriving in lockstep with low-energy cousins across billions of light years tell us any grain must preserve Lorentz symmetry to exquisite precision. Gravitational waves match general relativity's continuous predictions from black hole mergers, singing clean waveforms all the way to our detectors. Up here, the ramp works. Down there, the staircase waits. This is the deeper psychological hit. Singularities aren't just failures of calculus, they're pressure points on our intuition. We want reality to be like a scroll you can zoom forever. The infinities remind us that zoom is not a law of nature, it's a habit of thought. Where the continuum breaks, meaning must be rebuilt from new primitives. Quanta of area and volume, causal links instead of coordinates, boundary bits instead of interior fields. The infinities aren't the end of the story. They're the compass needle, twitching furiously, pointing at the door. Loop quantum gravity, quanta of area and volume. If the continuum tears, what does the thread look like? Loop quantum gravity takes that question literally and answers with a weave. It doesn't start by placing particles on a background. It starts by questioning the background itself. Suppose geometry, lengths, areas, volumes, isn't continuous. Suppose it's quantized the way energy is quantized in atoms. Then space isn't a stage. It's a roster of relationships that add up to something we experience as distance and shape. The formal root in is called a background-independent quantization of general relativity. Translation: you don't assume a fixed grid and then fit gravity into it. You let gravity define the grid. Mathematically, you recast Einstein's equations in a language of connections and fluxes, how fields thread through surfaces and around loops. Wilson loops, closed paths tracing the gravitational connection, become the basic observables. When you quantize those, geometry itself inherits quantum properties. The result looks nothing like a rubber sheet. It looks like a graph. Edges and nodes labeled with spins, half-integers that track how much quantum area an edge carries and how much quantum volume a node encloses. This is a spin network. From a distance, a dense network feels like a smooth region of space, the way a woven fabric feels like a single sheet when you rub it with your hand. Up close, you see threads. Here's the shocker baked into the math. Area and volume operators in this theory have discrete spectra. There are smallest non-zero eigenvalues. That means a surface can't have arbitrary area. It has to be an integer combination of tiny Planck scale tiles set by h stroke, c, and g. A chunk of space can't have arbitrary volume. It's counted in fundamental units. No half tiles. No infinitesimal leftovers. If the holographic hints tempted you, loop quantum gravity quantifies them. Bits per Planck area aren't poetic. They're how the world tallies geometry. How does time move in a world built from counts? Not as a universal flow. The network changes by local moves, edges split, nodes merge, labels rearrange, one discrete transition at a time. Stitch those transitions into a history and you get a spin foam, the four-dimensional record of how the network evolved. It's not that time is pixels, exactly. It's that change comes in quanta. Between one configuration and the next, there isn't a smooth in-between. There's a probability amplitude for a jump. This discreteness isn't slapped on. It's enforced by background independence. If there's no fixed lattice in the sky, you can't violate Lorentz symmetry with a preferred frame. The network's labels don't live in a rigid grid. They live in relations, and the large-scale behavior, averaged over many quanta, recovers the symmetries we test with gamma-ray bursts and gravitational waves. In other words, the microstructure can be grainy without making high-energy photons stumble, because there is no absolute notion of moving through the grains. Does this cure singularities or just decorate them? In simplified loop quantum cosmology, you can solve the dynamics of a homogeneous universe with quantized geometry. As densities approach the Planck scale, the quantum discreteness contributes an effective repulsion. Instead of scale factors sliding to zero, it hits a minimum set by the smallest volumes and bounces. The bang becomes a bounce. Is that the universe's true history? Not proven. But it shows how having no volumes below a certain size can block the infinities that plague the continuum. The same logic sharpens around black holes. Classically, horizon area is continuous. In loop gravity, horizon area comes in quantized steps. That lets you count microstates consistent with a given macroscopic area. Do the combinatorics and you recover the Beckenstein-Hawking entropy proportional to area in Planck units, with model-dependent refinements in the coefficient. That's not a hand wave. It's a calculation that ties the bits on the boundary to the network's punctures, edges that pierce the horizon and contribute quanta of area. What about ordinary space? The room you're sitting in, the air you breathe. If space is grainy, why don't we hear the rattle? Because the pixels are astronomically small and fantastically numerous. Like water molecules in a cup, their collective behavior averages to the smooth equations of hydrodynamics, which here are Einstein's field equations in the right limit. That's the key promise. Start with quanta of area and volume and recover the continuum as an emergent approximation when you stop asking microscopic questions. Meanwhile, the theory must respect every observational constraint. High-energy photons arriving in sync. Check. No rigid lattice to privilege one wavelength over another. Gravitational waveforms matching general relativity's predictions. Check. Coarse-grain the foam and you get classical waves propagating on the emergent geometry. Lorentz invariance tested to absurd precision. Check. Symmetry restored statistically, the way a turbulent fluid can still honor conservation laws. The psychological flip here is subtle. Loop quantum gravity doesn't tell you space ends at the Planck length. It tells you space counts at the Planck length. You can't divide forever because there's nothing to divide, only fewer quanta to count. The urge to imagine a last tiny bead you could hold in your fingers misleads you. The bead is a relationship in a network, not a fragment of stuff in a void. And that network isn't floating in space. It is space. Between the nodes are not miniature vacuums. They are the absence of relation. Add an edge and you've created adjacency, made 2 degrees of freedom neighbors. Change the spins and you've changed areas. Rearrange the graph and you've deformed geometry. In this picture, where is bookkeeping for how quanta are connected, and when is the story of how those connections change? If the continuum was a story we told about smooth fabric, loop quantum gravity hands us the loom. Strings, branes, and the holographic hunch. There's another path to the edge of reality, and it starts by giving up on points entirely. In string theory, the elementary dot of physics is stretched into a one-dimensional filament that vibrates. Different vibrations play different notes. One mode looks like an electron, another like a photon, another, crucially, behaves like a graviton, the quantum of gravity. That last note matters because it means gravity isn't bolted on, it's baked in. And because strings have size, roughly near the Planck scale, you can't meaningfully talk about distances smaller than the string's thickness. Try to sharpen your probe, you just excite the string and it swells. The point dissolves by design. But strings rarely travel alone. In the fuller picture, there are branes, membranes of various dimensions that strings can end on or wrap around. A 1 brane is a string. A 2 brane is a surface. Higher dimensional branes are like sheets and volumes. Our observable universe could itself be a 3 brane, with matter and forces confined to it while gravity seeps through extra dimensions. Extra dimensions aren't window dressing here. They're required by the math for strings to be consistent. Most are compactified, folded so tightly you don't notice them at human scales. Their geometry affects how strings vibrate, which sets the particle spectrum we see. Change the fold, change the notes. Here's the twist strings add to the Planck frontier: dualities. They're mathematical equivalences that say this description at very short distance is the same as that description at long distance. T-duality, for example, relates a circular dimension of radius r to one of radius 1r, with winding modes swapping places with momentum modes. Translation: dive below a certain scale and you emerge on the other side wearing different labels. The notion of shorter than Planck starts losing purchase, not because you hit a brick wall, but because the map loops back on itself. Then came a leap that tied all these hints together into a single principle. Studying black hole entropy, Jacob Beckenstein and Stephen Hawking found a formula that said, the maximum information inside a region scales with its boundary area in Planck units, not its volume. That's bizarre if you trust the continuum. It's natural if reality's bookkeeping lives on surfaces. Gerard T. Hooft and Leonard Susskind pushed that idea toward a radical claim, a holographic principle. All the physics inside a volume can be encoded on the boundary that surrounds it, like a hologram carrying a three-dimensional scene on a two-dimensional film. That sounded like poetry until Juan Maldacena wrote down a concrete dictionary in 1997. It's called the AD-SCFT correspondence. On one side, a theory of gravity in a higher dimensional de Sitter spacetime. On the other, a conformal field theory without gravity living on the boundary of that spacetime, one dimension lower. Every field in the bulk maps to an operator on the boundary. Every black hole thermodynamic quantity matches a thermal property in the field theory. Geometry over here is encoded as quantum entanglement over there. It's not our universe's exact geometry. Our cosmos isn't AD-S, but it's a working lab where holographic universe is a calculable sentence. The psychological punch is immediate. If the interior is fully captured by boundary data, then space inside might be an emergent way of organizing relationships among boundary degrees of freedom. The more entangled two regions are in the boundary theory, the closer they sit in the emergent bulk geometry. Cut entanglement and bridges of space pinch off. That isn't a metaphor. Tensor network toy models and results like the Ryu-Takayanagi formula tie entanglement entropy of a boundary region to the area of a minimal surface in the bulk. Area in Planck units counts information again. The Planck pixel shows up as a unit of boundary capacity. Even black hole puzzles start to look less paradoxical. If the boundary field theory evolves unitarily, the bulk cannot truly lose information. Hawking radiation that looked thermal from afar must carry correlations the bulk description had smeared. Page curves computed holographically show entropy rising, and then falling as expected if information eventually escapes. We're not done. The fine print involves quantum extremal surfaces and replica tricks. But the trend is clear. When gravity is holographic, inside becomes a story told by outside, and the book keeps its pages. What about Lorentz invariance? The worry that any grain would slow hard light. Holography dodges the trap. There is no rigid bulk lattice. The boundary theory can respect exact Lorentz symmetry, and the emergent bulk inherits it in the appropriate limit. High-energy gamma rays crossing billions of light-years arrive in lockstep because the smoothness is an emergent symmetry of the coarse view, not a property of microscopic tiles strewn in a preferred frame. Strings add one more safety rail, minimal length without violating symmetry. Because a string size grows with energy, your attempt to probe shorter scales feeds back. Combine that with dualities and you get an operational floor set by H-stroke, C, and G, not by a naive crystal of space. The story rhymes with loop quantum gravity's quanta of area and volume, but the grammar differs. Loop quantizes geometry directly, building space from spin networks. String theory keeps smooth geometry in the bulk, but replaces point particles, enforces a minimal length through extendedness and duality, and then, via holography, whispers that the geometry itself is a code. Meanwhile, experiments keep setting the guardrails. Gamma-ray bursts show no energy-dependent speed lag within our precision. Gravitational waves match general relativity's waveforms. If reality is holographic, it hides its pixels well. Encoded as bits per Planck area on screens we don't yet know how to read directly. But the principle keeps paying rent. It resolves paradoxes, stitches quantum and gravity into one fabric, and reframes the Planck scale not as a final zoom level, but as the native resolution of the code that renders spacetime. Information bounds, Beckenstein-Hawking and the bit budget. If space is code, there has to be a memory limit. The clues came from a strange place, the bookkeeping of black holes. In the early 197s, Jacob Bekenstein asked a heretical question for the time. If black holes obey thermodynamic laws, what is their entropy? Entropy counts microstates. How many internal configurations fit the same outward look? Classically, a black hole had no hair, no visible structure. Yet Stephen Hawking's later calculations showed black holes radiate with a temperature. Temperature without entropy makes no sense. So Bekenstein proposed a bound, the maximum entropy S that can be crammed into a region of space with boundary area A is proportional to that area measured in Planck units. Not the volume, the area. Hawking's quantum field calculation near the horizon nailed the coefficient. The Bekenstein-Hawking formula reads S equals A, 4-letter 2113P2, setting Boltzmann's constant to 1. Translate entropy to information. 1 bit is roughly ln2 of entropy. So a patch of horizon with area equal to 4 Planck area stores about 1 bit. That's the first hard statement that nature counts bits per Planck area. It's a capacity limit written in geometry. Bekenstein didn't stop at horizons. He framed a universal bound. For any system of total energy E confined to radius r, the entropy satisfies S less or equal to 2 pi r/h/c. Try to cheat, pack more states in without raising energy or size, and the bound says no. If you do raise energy, you flirt with gravitational collapse, forming a black hole whose area-based entropy caps your ambition anyway. Either way, gravity enforces an information budget. But the cosmos is not just static spheres. It's dynamic, curved, sliced by light. Raphael Bousso took the area idea and made it covariant, valid in any spacetime, regardless of how it's warped. Draw any two-dimensional surface. From it, shoot light sheets, families of light rays that move away from the surface with non-positive expansion. That is, their cross-sectional area doesn't grow along the congruence. Bousso's covariant entropy bound says the total entropy passing through any one of those light sheets is bounded by a quarter of the area of the starting surface in Planck units. You don't need a horizon. You need geometry and causality. The bound travels on light. This is not a numerology trick. It survives every test we've thrown at it. In cosmological spacetimes, in gravitational collapse, in exotic matter distributions consistent with energy conditions, the bound holds. Where it seems to fail, so do the assumptions that permit it. It's a rule nature respects when we respect the inputs of general relativity and quantum field theory. What does that mean for ordinary space? Take a cubic meter of air. If the continuum were literal, you might imagine stuffing an infinite amount of information into smaller and smaller ripples of fields inside. But Bekenstein, Hawking, and Bousso slam the door. The information you can extract from that region, no matter how clever your encoding, is limited by the surface area, not the volume. You can add atoms, photons, structure. Past a point, to double your bits you have to double your boundary. Or you'll collapse your lab into a black hole that obeys the same area law and sends your plans up in Hawking radiation. Here, S where the holographic principle stops being a metaphor and starts being a necessity. If the maximum information in a region scales with its boundary, then a full description of the physics inside should exist on that boundary, with roughly 1 degree of freedom per Planck area patch. That's exactly what AD-SCFT realizes in a special spacetime. A boundary field theory, finite in its local information density, encodes a bulk with gravity. Balso's bound ensures that even away from that special case, the bookkeeping can't exceed the area budget. The pixels might not be literal squares on a lattice, but the bit count is geometric and finite. This bit budget has teeth. It tells you why a naive continuum field theory has too many degrees of freedom to be the last word. It tells you why quantum gravity must tame ultraviolet infinities. A theory that lets you hide arbitrary information in vanishingly small volumes would violate the area law once gravity is turned on. It sharpens black hole paradoxes into accounting puzzles. Track the bits across light sheets and horizons, and you'll demand unitary evolution in any complete theory. It also reframes cosmic questions. In an expanding universe, horizons appear, cosmic event horizons in accelerating spacetimes, apparent horizons in collapsing regions. Each comes with an area and thus an information cap. If spacetime's rendering resolution is set by Planck areas on these screens, then the smooth interior we trust is a compression algorithm that never exceeds the bound. Entanglement becomes the currency that pays for geometry. Cut the entanglement across a boundary, and you reduce its area in Planck units, literally deflating the space it encloses. Psychologically, there's a gut punch here. We want reality to be infinitely articulate, with infinite detail hiding in every nook if only we zoomed in far enough. The Beckenstein-Hawking story says no. The universe is generous but not infinite in its local detail. There is a ledger. It's written on surfaces, and every time you try to draw more within, gravity edits your draft back down to the allowed number of bits. The experimental chase. Where could pixelation show up? If space has a native resolution, where would the seams show? Not in a lab bench microscope. Our best accelerators fall 19 orders of magnitude short of Planck energies. So the hunt moves to natural machines and subtle telltales, places where the universe does the heavy lifting and we just read the printout. Start with the sky's flashbulbs, gamma-ray bursts. When a star collapses or neutron stars collide, they hurl photons across billions of light years. If spacetime were a crude lattice, high-energy photons with tiny wavelengths should feel the texture while low-energy photons glide. They'd arrive slightly out of sync after their marathon. We looked. Observatories like NASA's Fermi and the Magic telescopes timed the sprints. Within our sensitivity, arrival times match. That tightens the vice on any model that breaks Lorentz invariance with a simple grid. If there are pixels, they either preserve symmetry delicately or hide behind dynamics that cancel the lag. Now listen instead of look. Gravitational waves, space's own vibrations, carry the signatures of black hole and neutron star mergers. If geometry were granular, you might expect dispersion, different frequencies traveling at slightly different speeds, waveforms fraying over cosmological baselines. LIGO and Virgo recorded chirps from over 1 billion light-years, and the sweeps match general relativity's continuous prediction to brutal precision. No frequency-dependent slippage shows up in the bands we can hear. That doesn't exile discreteness. It says the continuum is an excellent large-scale approximation. A good fluid doesn't betray its molecules in every ripple. What about laboratory tricks? If you can't climb to Planck energies, maybe amplify tiny effects with coherence. Atom interferometers split matter waves and recombine them, sensitive to minute phase shifts. If some Planck scale jitter added universal noise, it could decorrelate fringes over long baselines. So far, interferometers behave like the Schrödinger textbooks promise. Optical cavities, too, trap light bouncing millions of times between mirrors. Any stochastic holographic noise that shakes the cavity length at Planck scales would plateau sensitivity. Experiments like the Fermilab holometer aimed at precisely that. No excess fuzz beyond known noise sources surfaced. Ambitious ideas, hard negatives. Cosmic microwave background photons cross the entire visible universe to reach us. If spacetime's fine structure imprinted anisotropies or preferred directions, we might see tiny violations of statistical isotropy, or a frequency-dependent blurring inconsistent with known foregrounds. The Planck satellite mapped the sky with exquisite detail. Its name nods to the scale we crave, but its data mostly tighten the leash. The temperature and polarization patterns fit a smooth primordial plasma evolving on a continuous geometry. Within uncertainties, no Planck scale graffiti. Then again, not all signatures are timing games. Black holes themselves are thermodynamic objects. If horizon area is quantized in tiny steps, the late-stage evaporation spectrum might have faint lines superimposed on Hawking's broad thermal glow. That's far beyond current telescopes. Astrophysical black holes are too cold primordial ones, if they ever formed, too speculative and faint. The James Webb Space Telescope won't spot Planck pixels. But tabletop analogs, sonic black holes in Bose, Einstein condensates, simulate horizon physics. They've produced Hawking-like radiation in media with built-in microstructure. It doesn't prove gravity's grains. It proves the mechanism can survive a non-continuum. That's a sanity check many theorists demanded. Neutrinos offer another path. These ghostly particles cross matter and magnetic fields unbothered, logging long baselines. If Planck scale effects tweak dispersion or induce tiny violations of CPT symmetry, the oscillation patterns between flavors might shift with energy in odd ways. IceCube has watched PV neutrinos from deep space. The oscillations behave, but the energy reach is climbing, and future detectors could turn neutrinos into rulers that test the symmetry of the stage rather than the actors. High-energy cosmic rays slam into the atmosphere carrying more energy than we can make on Earth. If spacetime granularity modified thresholds for particle production, say the Greisen, Zatsepin-Kuzmin cutoff for protons interacting with the cosmic microwave background, the observed spectrum would kink differently. The Pier-Auger Observatory and telescope array see the expected suppression. No anomalous leak across the cutoff that a naive grain might cause. Another guardrail, another narrowed corridor. There's a subtler clue that keeps resurfacing. Entanglement as geometry's glue. If the holographic principle is more than a slogan, then patterns of quantum entanglement across a boundary encode area in Planck units. That's not something you photograph. It's something you infer from consistency. Add SCFT computes page curves, the entropy history of evaporating black holes, and gets the unitary answer only when you include quantum extremal surfaces, a geometric proxy for information flow. That's a test of a principle, not a direct peek at pixels, but it's the kind of evidence that builds a case in a domain where microscopes fail. So where could pixelation show up next? In correlations rather than delays, in noise floors that refuse to sink below a calculable bound, in precise phase comparisons between clocks separated by long baselines if spacetime fluctuations tie their ticks together. Space-based interferometers like LISA will extend gravitational wave hearing to lower frequencies and longer paths. Next-generation gamma-ray observatories will time higher energy photons with finer stopwatches. Neutrino astronomy will leave its adolescence. Each expands the lever arm a little farther. Meanwhile, particle colliders won't reach the Planck energy, but they do test principles the Planck story leans on: Lorentz invariance, locality, unitarity. If a theory of quantum gravity predicts tiny violations, precision measurements at modest energies can rule them out. So far, the symmetries hold. That's not boring, it's instructive. It tells us the Planck scale structure, if real, is encoded in a way that respects the large symmetries almost exactly, the way a crystal can look isotropic when you average over grains. The psychological lesson carries through the data. The universe keeps meeting us with silence where we expect crackle. No lags, no fuzz, no obvious seams. That silence doesn't mean the pixels aren't there. It means the rendering engine is good, and it reframes the chase. We're not just looking for a glitch. We're learning which glitches nature forbids, and in that negative space, the shape of the code begins to appear. Double slit to double take, quantum limits meet gravity. Start with the most disarming experiment in physics: 2 slits, a dim light, and a screen. Fire photons one at a time. Instead of 2 neat piles behind the slits, you get an interference pattern, bright and dark bands like ripples crossing on a pond. It means each photon behaves like a wave spread across both paths, interfering with itself. Now place detectors to ask which slit it actually used. The pattern vanishes. You traded interference for which path knowledge. The act of measurement reshaped the outcome. That's the first limit. To sharpen knowledge of position, you must interact. Interactions cost disturbance. Heisenberg didn't make that up as a measurement flaw. It's baked into the world. The uncertainty principle links spreads in position and momentum by a constant, Planck's h-stroke. Make the slit narrower, position tighter, momentum blurrier. The wave packet fans out faster because you forced it to be localized. Quantum mechanics turns seeing into changing. Now push the logic past classroom optics. Replace visible light with higher energy probes so you can pinpoint location more precisely. A shorter wavelength photon marks a position more tightly. By E equals h-stroke omega, it also carries more energy. Fire it at an electron, and you can in principle locate the electron within about the probe's wavelength. But that energy goes somewhere. At sufficiently high energies, your photon can knock new particles out of the vacuum. Pair production becomes easy. Measurements spawn matter. The double slit's gentle interrogation becomes an industrial-grade collision. Fold gravity into the conversation and the story tilts. Energy curves spacetime. The more energy your probe carries in confines, the more it strains the geometry. If you try to confine an electron's wave packet to a region smaller than a certain scale by hammering it with ultra-short wavelength quanta, you inflate the local energy density. There's a threshold where that density no longer just jostles your target. It digs a hole in spacetime deep enough to capture light. You didn't resolve a smaller feature. You engineered a horizon. The double slits measure and disturb becomes measure and collapse. You can make this concrete without mystical hand waving. The reduced Compton wavelength, h//mc, is the quantum scale tied to a particle's mass m, the length below which localizing the particle reliably triggers particle creation in standard quantum field theory. The Schwarzschild radius, 2gm/c2, is the gravitational scale where mass m wrapped inside that radius would be a black hole. Equate a localization length with a gravitational radius, and you land near the Planck length. It's the crossover where the two stories, quantum delocalization and gravitational collapse, speak the same language. Below that, position stops being a classical coordinate you can refine with better optics. It becomes a question without an operational answer. So what does a gravity-aware double slit even mean? Imagine building a slit apparatus with Planck scale features. Quantum mechanically, your particle's wave still tries to sample both paths, but the slits themselves are masses with edges and supports. Each path adjustment drags geometry with it, however faintly. The metric becomes a participant, not a stagehand. The phase that drives interference now includes gravitational phase, tiny in normal life, mandatory at extreme confinement. Push toward the Planck regime, and the coherent superposition of went left and went right must also be a superposition of slightly different spacetimes. That's not a poetic flourish. It's what gravity is geometry demands. Here's the double take. In ordinary quantum mechanics, you can always scale down and expect your wave to explore both slits more crisply with better isolation. In the gravity-aware world, scaling down is self-defeating. The refinement tool becomes the source of curvature that erases the path information you hope to control or buries the region behind a horizon. In place of more careful, you need more clever. Encode information in entanglement, not position. Ask boundary questions, not interior ones. Does that kill interference at human scales? No. Interference thrives in labs because masses are small, geometries barely budge, and environmental noise is the bully long before gravity. But conceptually, the horizon of knowability sits not at our engineering limit, but at nature's, set by h stroke, c, and g. The double slit teaches you that observation costs. Gravity teaches you there's a currency exchange rate you can't beat. Convert too much precision into energy in too small a region, and spacetime charges interest as curvature. This reframes the Planck scale as a principle, not a gadget. The universe is telling you questions that demand sub-Planck localization are ill-posed. Ask about relational data: who is entangled with whom, what flux crosses a surface, how boundary bits count. The interference pattern you can still trust at any scale is not in positions through slits, but in the consistent stories different observers tell when they respect the code's resolution. That's the grown-up version of the double slit lesson, with gravity in the room. Emergent spacetime. Entanglement builds geometry. We've been circling one unsettling idea. Maybe space isn't fundamental. Maybe it's the scoreboard, not the game. If so, what plays the game? The sharpest candidate is entanglement, the quantum linkage that makes two systems behave as one, no matter how far apart they sit in our everyday picture. Flip the perspective, and entanglement isn't acting in space, it's building it. Here's the cleanest laboratory where this braids into math, not metaphor. In holography's add SCFT dictionary, a boundary quantum system with no gravity encodes a bulk spacetime with gravity. Now take a region on the boundary and ask, how much quantum information inside it is entangled with the rest? The answer within that correspondence is geometric. It equals the area of a special minimal surface hanging into the bulk, measured in Planck units. That's the Ryu-Takayanagi relation. Translated, the more entanglement across a cut in the boundary, the larger the area of the bulk surface tethered to that cut. Area counts bits again, but now bits cause area. Push that logic and the bulk shape stops being a given. It becomes a bookkeeping device for patterns of entanglement. Stitch two boundary regions together with strong entanglement, and the emergent bulk brings them close. Sever the entanglement and the emergent distance grows. Bridges of geometry thin and snap. Toy tensor networks make this vivid. You wire qubits into a web of perfect tensors, a circuit that spreads entanglement across layers. Viewed from afar, the network looks like a discretized bulk where geodesics through the web approximate minimal surfaces. The boundary's quantum state programs the interior's shape. This isn't only eye candy. It pays off where gravity is hardest, black hole evaporation. Track the entropy of Hawking radiation, the Page curve, and you expect it to rise as the hole spits out seemingly thermal quanta, then turn over as correlations begin to dominate, returning information to the outside. Holographic calculations recover that unitary curve by adding quantum extremal surfaces, surfaces whose area plus an entanglement term is minimized. The upshot is blunt. When you count the right boundary entanglement, the bulk respects unitarity. No information disappears. It migrates through entanglement and the geometry adjusts. Now strip away ADS's special curvature and look for principles that don't depend on that sandbox. One keeps surfacing. The bit budget lives on surfaces, not volumes. If area in Planck units tallies capacity, then local geometry must be an emergent compression of correlations. In that sense, Einstein's equations could be like thermodynamics, effective laws that emerge when you average over microstructure. That's not hand-waving. There are derivations that start from entanglement equilibrium, tiny variations in entanglement across small balls, and land on linearized gravitational dynamics. Make entanglement extremal, get curvature equations. It's a whisper. Gravity is the elasticity of entanglement. Meanwhile, loop quantum gravity offers a complementary lens. There, the bulk is a spin network, and the boundary is literally punctured by edges carrying quanta of area. Count the ways those punctures can arrange to yield a given macroscopic area, and you recover the Beckenstein-Hawking entropy scaling. You're again tying geometry to counts, microstates on a boundary matching a smooth horizon outside. Different math, same refrain. Area counts entanglement, and entanglement builds area. What about time? If where is a ledger of connections, when is how that ledger updates. In holography, unitary time evolution in the boundary scrambles and redistributes entanglement. In the bulk, that reads as geometry flowing, surfaces shifting, volumes swelling, wormholes stretching or shrinking as patterns of correlation morph. The equals Epper conjecture goes bolder. Entangled pairs and non-traversable wormholes could be two descriptions of the same thing. Not portals for travel, but blueprints for how connectivity in quantum information translates to connectivity in space. Build entanglement, grow bridges. Cut entanglement, pinch them off. You can test the spirit of this without Planck firepower. In many body systems, entanglement isn't decoration. It governs phase structure, transport, thermalization. Quantum simulators now weave artificial geometries by programming who entangles with whom. The more we learn, the clearer the pattern. Organize information flow, and you organize the effective notions of distance and adjacency. Gravity's trick may be that the code runs at a resolution where C, G, and H stroke fix the pixel size, and the continuum equations we love are the hydrodynamics of that code. Why does this matter psychologically? Because it flips our instinct. We're used to thinking space contains entanglement. The better sentence is entanglement contains space. You don't ask what's in between two particles to explain their correlation. Their correlation is what creates the sense of in between. The Planck scale then stops being a tiny brick. It's the unit in which the ledger balances. One Planck area, one bit of capacity. Fill the ledger with the right pattern of links, and a smooth metric appears. Change the pattern and the map redraws. We set out asking whether reality has pixels. This is the grown-up answer. If it does, they're not pellets of stuff. They're units of relation. The picture you and I move through, rooms, streets, stars, is the macroscopic rendering of a deeper circuit that roots entanglement at Planck limited bandwidth. And the cleanest hint we're on the right track is that when we let information lead, geometry follows. The frame rate question, Planck time and causality. If space counts in Planck areas, what about time? Does it tick? The temptation is to say yes. Take the Planck time, about 5.4 times 1044 seconds, and call it the universe's frame rate. One cosmic shutter closing and opening, click by click. It's intuitive and it's wrong in a subtle way. A fixed global frame rate would pick a preferred cosmic clock and violate relativity's most reliable rule. No observer gets the special watch. Yet the Planck time still matters, not as a universal metronome, but as a limit on how tightly events can be meaningfully separated. Think of causality as the universe's traffic law. Nothing outruns C, and effects must sit inside the future light cone of their causes. Now ask, how close can two distinct causes be and still be distinct, once gravity and quantum jitter are both loud? Below a Planck time apart, the energy needed to stamp two events that tightly into the record curdles the record itself. The ink you use to write the ticks bends the page. So Planck time is not a tick-tick-tick for everyone. It's the shortest interval for which a clean causal statement can be operationally made by anyone. That answers one misconception and raises another. If time isn't globally discrete, how does discreteness in loop quantum gravity or holography avoid a stutter in motion? By making change local and relational. In spin foams, transitions happen in discrete steps, but not in lockstep across the cosmos. Different parts of the network update in different orders that all agree on cause and effect when you zoom out. It's like distributed computing with no master clock. As long as messages respect light cones, the system reaches the same consistent state regardless of update timing. Causality is the constraint. Planck time is the granularity beyond which the constraint can't be sharpened. What about the arrow of time? The fact that tea cools, eggs break, and we remember yesterday, not tomorrow. The Planck scale doesn't set that arrow, entropy does. But it bounds how fast entropy can flow across a boundary. Boussow's covariant bound, measured in Planck areas, limits the information, and thus the entanglement, crossing any light sheet. In that sense, the Planck time and area together act like bandwidth caps for reality's data transfer. You can't send more than about 1 bit per 4 Planck areas per Planck tick across a horizon-sized screen without triggering gravitational backreaction that rewrites the screen. Holography sharpens the picture. On the boundary, time evolution is unitary, no frames dropped. In the bulk, that same evolution reads as geometry changing smoothly when you coarse grain and discretely in the deep code. The Ryu-Takayanagi prescription ties how much time has passed to how much entanglement has been rearranged via areas of minimal surfaces in Planck units. The more you scramble, the more the bulk stretches. The Planck time doesn't chop boundary unitarity into slices. It sets the smallest meaningful delta in the bulk's entanglement geometry ledger. Then there's signaling. If spacetime had a naive frame rate, you might worry that causal order could flip at high energies, or that two events within a Planck tick might ambiguously influence each other. But the light cone survives because the symmetries survive. Any acceptable quantum gravity must reproduce Lorentz invariance to the precision we've tested. Gamma-ray bursts arriving without energy-dependent lag, gravitational waves keeping phase over cosmological distances. That's not an accident. It's the emergent consequence of microdynamics that respect causal structure, even as they quantize the bookkeeping beneath it. So should we ever talk about a last tick? Only in an operational sense. If you propose two events separated by less than a Planck time, you owe the universe a way to witness that separation without building a device whose energy density collapses your lab into a horizon. You can't. That's the principle hiding in the math. It doesn't tell you time is built from identical slabs. It tells you there's a resolution limit on causal statements enforced by H stroke, C, and G below it. Before and after smear into a quantum superposition of possible stories that no observer can sort with agreement. Here's the human angle we can't escape. We want the world to play like film, frames flicking by. At the Planck edge, the better metaphor is a live stream over limited bandwidth. Packets arrive in a way that preserves order and content within the channel's capacity, but there is no universal slice count behind the scenes, only constraints that keep the stream coherent. Planck time is the bitrate of causality, not the projector's click. Black holes as bouncers, no entry beyond this scale. Think of black holes as the universe's most uncompromising bouncers. There's a guest list written in constants H stroke, C, and G, and if your question tries to slip inside with sub-Planck precision, the door doesn't just close. A horizon appears. No appeal, no wristband. The party you wanted to inspect is now hidden behind a one-way boundary. Here's how the velvet rope gets pulled. To resolve a smaller detail, you bring shorter wavelength probes. Shorter wavelengths carry higher energy per quantum, E equals H stroke omega. Focus that energy into a tiny region and general relativity responds, energy curves spacetime. Push past a threshold set by G and C, and your focal spot crosses its own Schwarzschild radius. You didn't build a better microscope. You built an event horizon. Add more energy, and the horizon swells, pushing information further out of reach. Your curiosity fuels the very thing that blocks it. This isn't just clever rhetoric. It's a quantitative rule. There's a clean way to see the no-entry sign using two lengths that hate each other. The reduced Compton wavelength, H/MC, marks how tightly quantum theory lets you localize a particle of mass m before particle creation muddies identity. The Schwarzschild radius, 2gm/c2, marks how tightly gravity lets you pack mass before it hides behind a horizon. Slide m so those two lengths meet and you land, up to order 1 factors on the Planck length. Below that scale, the quantum rule, localize more precisely by using more energy, triggers the gravitational rule, more energy means a bigger radius of no return. The bouncer doesn't argue, it enforces. Horizon physics turns that enforcement into arithmetic. Beckenstein-Hawking showed a black hole's entropy is its horizon area divided by 4 Planck areas. That's a bit budget. about 1 bit per 4-letter 2113p2. When your measurement collapses into a horizon, you've traded access to interior detail for boundary pixels. The bouncer stamps your hand with area. You can't redeem it for volume again. Try to hide more information inside a fixed boundary, and gravity raises the entry fee. The hole grows to keep the ledger balanced. Even the radiation that leaks from the club follows the rules. Hawking radiation is thermal at first glance, set by surface gravity and H-stroke. If evaporation ended in pure heat with no correlations, UD break quantum unitarity, like shredding the guest list. The modern holographic answer says the list is stored on the boundary, and the radiation carries subtle correlations that a coarse view washes out. Recent page curve calculations using quantum extremal surfaces support that story. Entropy rises, then falls, consistent with information leaving. The bouncer isn't losing track, it's scanning everyone. Notice what this means for smaller than Planck. It isn't that there's a literal last atom of space you could scrape with your fingernail. It's that any operational attempt to access sub-Planck detail converts your device into a horizon that downgrades the question into boundary data. The scale at which that happens is set by H-stroke. C and G change your strategy. More energy, sharper pulses, heavier probes, and you only make the horizon more efficient. The door gets thicker. This boundary bookkeeping isn't optional. Try to stuff more than a slash, 4-letter 2113p2 bits through a light sheet flowing off a surface, and you violate Boussow's bound. The correction comes automatically. Back reaction bends the light sheet, collapses your channel, or inflates the boundary until the inequality is safe. The bouncer isn't a person at the rope, it's geometry enforcing consistency between information and curvature. If that sounds abstract, tie it to something time-stamped. We've seen black hole mergers with LIGO and Virgo. The ring-down phase, the dying tones as the horizon settles, matches general relativity's smooth predictions with no telltale dispersion. That's the large-scale song of a surface that counts in Planck units yet behaves like a drumhead from afar. No stutter, no lattice echo, just a clean waveform from a boundary that's already priced the pixels into its tension. And if you want a lab rehearsal, condensed matter physicists have built sonic horizons in ultra-cold gases. They aren't gravity, but they do show Hawking-like radiation emerging from a system with microscopic constituents. The message is modest and sharp. Horizon thermality doesn't need literal continuity. A well-behaved coarse graining can hide atoms and still sing the right thermodynamic tune. That's a stress test the bouncer picture passes. Psychologically, here's the sting. We're wired to believe that more effort, more power, more focus always pierces deeper. Black holes embed the opposite lesson into the rules. Past a point, more power buys less access. Turn up the spotlight and you summon the guard who shuts the door. At the Planck threshold, curiosity stops being a crowbar and becomes a construction crew for horizons. So what do you do when the bouncer won't budge? You change the question. You ask boundaries, not interiors. You count bits per Planck area instead of modes per cubic meter. You track entanglement across horizons rather than trajectories through singularities. You use C, G, and H-stroke as the venue's fire code, not as decorations on the wall. Because at this club, the rule is you can't come in. It's you've been looking in the wrong place. The action is on the door. Continuum as effective theory. Why calculus still works. After all this talk of pixels and Planck fences, it's fair to ask a simple question. If space counts in quanta, why does calculus work so well? Why do smooth curves, derivatives, and differential equations predict eclipses to milliseconds, antennas to millimeters, and GPS to meters? The short answer is scale. The long answer is that smoothness is an emergent language. The way temperature is a perfectly good word even though no single molecule has it. You don't measure a fever by watching one atom, you average over trillions. Space plays the same trick. Think about water. At kitchen scales, you stir it and see a continuous flow. At molecular scales, it's a chaotic swarm. Hydrodynamics is the effective theory that emerges when you stop caring about each molecule and care about conserved quantities, mass, momentum, energy, and how they move. Navier, Stokes equations don't know molecules exist. Their job is to be right when you're far enough away from the microstructure. Einstein's field equations and Maxwell's equations sit in the same role for spacetime and fields. They're the hydrodynamics of geometry and electromagnetism when you're averaging over unfathomable numbers of Planck units. Effective field theory formalizes this. It says, pick an energy scale, integrate out the degrees of freedom above it, and describe the rest with a handful of fields and couplings. You don't need to know quark details to design a bridge. You encode the high-energy mess into renormalized parameters and higher-order corrections suppressed by powers of your cutoff, here, by the Planck scale. As long as your experiment's wavelengths are large compared to LP, the corrections are tiny. That's why gamma rays and gravitational waves travel cleanly. The leading terms, the continuum ones, dominate. Even if space is built from quanta of area and volume, the numbers crush the discreteness into silence. A cubic centimeter of air contains roughly 1023 molecules. A region of space, a cubic centimeter across, would contain something like 1099 Planck volumes. Averaging over that many units obliterates grain in practice. The spin network's graph becomes an elastic medium. The holographic boundary's pixels become a smooth screen. Calculus works because the sums over tiny steps converge to derivatives when you have stupendous numbers of steps. There's another layer, symmetries, Lorentz invariance. The statement that physics looks the same to all inertial observers acts like a guardian. Many naive discretizations would spoil it by picking a preferred grid. But if the microstructure is relational, not a rigid lattice, and if the emergent large-scale behavior respects the symmetry, then the continuum laws that encode that symmetry are the right tools. That's why we see no energy-dependent lag in gamma-ray bursts. The effective description has inherited the symmetry to fantastic precision. Renormalization group flow tells you how this happens. As you coarse-grain, irrelevant operators, micro-level quirks fade. Relevant ones shape the physics you see. Gravity's coupling is weak at accessible energies, so quantum gravitational corrections to the equations that guide planets and light are utterly negligible. The Einstein-Hilbert action wins the low-energy contest. The corrections are there, suppressed by powers of EEP at LIGO frequencies and Fermi energies. EEP is so absurdly small you can forget it without remorse. This is why singularities signal a breakdown while orbits don't. When curvatures are modest and wavelengths long, the continuum holds. When densities press toward Planck values, the higher-order terms you normally ignore explode, and the effective description fails. You wouldn't trust hydrodynamics to describe a shock at atomic scales. You wouldn't trust classical geometry inside a Planck-thick throat. The theory tells you where it is trustworthy by the size of its neglected terms. Engineers live on this philosophy. A circuit designer treats copper as a continuous conductor because, at the frequencies and lengths of interest, electrons, grain doesn't matter. A meteorologist treats air as a fluid because molecules don't ruin the picture of pressure fronts and vortices. A cosmologist treats spacetime as a smooth manifold because at megaparsecs and gigayears, Planck tiles are invisible. When we calibrate a telescope's mirror, its curvature fits a polynomial. No one asks how many spin network edges pierce it. Even in quantum theory, continuity is a workhorse. Wave equations, path integrals, and differential operators describe probability flows that, at scales far above LP, feel and behave smoothly. The discreteness, if real, constrains the ultraviolet, not the infrared. It cuts off the infinities that would otherwise infect the high-energy end, but it doesn't infect the low-energy river that carries us. There's also compression. If the holographic principle is true, the bulk's detailed microstructure is efficiently encoded on a boundary with finite capacity, about 1 bit per 4 Planck areas. The interior's continuum picture is then a decompressed view of boundary data. Like a high-resolution video stream, you don't need to know pixel-by-pixel encoding to follow the plot. The codec guarantees smooth motion as long as the bitrate, set by Planck units across horizons, is respected. So calculus isn't a polite fiction. It's the correct effective grammar for the scales we inhabit. Derivatives, geodesics, curvature tensors. These are the right summaries when you average over obscene numbers of microscopic degrees of freedom. The Planck story doesn't cancel them, it crowns them. It tells you why they work so unnervingly well, where they will fail, and how another language, counting bits, tracking entanglement, summing discrete histories, must take over when you insist on asking questions beyond the code's resolution. Implications, limits, meaning, and the next experiments. If the code of reality runs at a Planck-limited resolution, two things follow. First, nature isn't promising infinite detail on demand. It's promising consistency. Second, progress won't come from brute force, but from asking questions that respect the ledger. Area counts, entanglement nits, causality budgets bandwidth. That sounds abstract until you translate it into experiments and meaning. Start with limits. The Beckenstein-Hawking bounds tell us there's a maximum bit rate across any light sheet set by area in Planck units. That caps compression tricks in quantum tech. You can't hide unlimited information in a cubic micron without paying gravitational interest. The holographic story reframes more qubits in less space as more boundary to hold them. That's not a buzzkill. It's a design constraint like the speed of light was for electronics that births cleverness. Quantum repeaters, error-correcting codes, and distributed architectures look less like hacks and more like the native way the universe routes information. It also shifts how we talk about meaning. If geometry emerges from entanglement, where it becomes a statement about correlations, that reorients puzzles about identity, locality, and cause. The impulse to ask what's really inside a black hole softens into boundary accounting. Who is entangled with whom, and how do those links evolve? Before the Big Bang transforms into how did the entanglement network rewire across a bounce or an emergent start? We stop demanding answers the code can't display and start learning its interface. So what next? You won't build a Planck accelerator, but you can probe the rules at long lever arms. Three frontiers stand out. Timing and dispersion. Gamma-ray burst already constrained simple grid models by showing no energy-dependent lag. Next-generation telescopes, CTA on the ground, and future MeV, GV missions in orbit, will clock higher energies with sub-millisecond precision. A single out-of-order photon won't prove pixels, but a pattern across events could carve away entire classes of Planck Scale models or hint at symmetry preserving dispersion too subtle to see today. Phase and coherence. Space-based interferometers like LISA will stitch 5 million kilometer arms into a gravitational wave ear. If any frequency-dependent phase creep or irreducible, holographic noise exists, longer baselines and cleaner environments are where it would whisper. Atom interferometers on Earth and in orbit push coherence times higher. If Planck-limited fluctuations set a hard noise floor, these devices will find it, or make the silence more impressive. Entanglement geometry. Holography's most testable spirit isn't a photon delay, it's the link between information and area. Quantum simulators, Rydberg arrays, superconducting qubits, trapped ions, now implement toy holographic codes. They measure entanglement growth, scramble patterns, and even reconstruct minimal surfaces in tensor networks. You're not building ADS in a lab, but you can verify the logic. When you tune correlations across a cut, a geometric proxy in the code changes as if area measured in bit units had flexed. That's the seed of entanglement builds space in controllable hardware. Neutrinos and cosmic rays add reach. IceCube Gen 2 and KM3NT extend the energy and distance rulers for dispersion, CPT tests, and threshold anomalies. The Pierre-Auger Observatory's successors refine the spectrum near the Greisen, Zatsepin-Kuzmin cutoff. Any Planck scale tweak to kinematics would show up as a mismatch in the ultra-high energy tail. So far, the sky votes for smoothness. The vote tally is getting sharper. On the theory side, the target is predictive grip. Loop quantum gravity must keep deepening its semi-classical limit. Show, not just argue, how spin foams coarse-grain to Einstein's equations, and how black hole microstate counting fixes coefficients beyond leading order. String theory must keep translating holography toward our universe. Less anti, de Sitter, more cosmology, more quantum extremal surfaces that compute page curves in time-dependent backgrounds. Causal set theory must cache in its clean causal grammar with signatures that survive coarse graining and respect Lorentz symmetry. Watch for cross-checks that tie principle to phenomenon. Quantum error correcting codes aren't just metaphors for holography, they're its working dictionary. If bulk locality is boundary redundancy, improvements in codes tell you how robust geometry is to noise, and how black holes can be both scramblers and memory devices. If entanglement equilibrium yields linearized Einstein equations, then deviations from equilibrium in many body experiments should mirror geometric strains in the dual. These are not Planck Scale sightings. They're consistency tests that narrow the space of viable codes. And then there's the human meaning. Limits don't shrink wonder, they focus it. The Planck ledger doesn't say stop. It says stop zooming and start asking better. It trades the fantasy of an endless microscope for the craft of decoding boundary screens, stitching entanglement into maps and reading geometry as information flow. That's not less reality. It's a clearer contract with the one we have. What we can say and what we can't. Here's what we can say. The data favor a smooth world at our scales, and the math points to a finite bit budget in Planck units, with entanglement as the bridge from information to geometry. Here's what we can. Name the final code. If you want more stories like this, subscribe and watch our deep dive on black hole page curves next. Then tell me where you think the pixels would show first.